All right, welcome back to these chemistry videos. Today we're going to talk about special reactions. These are going to be for those reactions that don't follow those simple patterns like A plus B turns into AB or AB turns into A plus B. We have to have different ways of figuring out what products would form. And so like I just said, there's some reactions that are more complicated, and that makes sense because there's tons and tons of different chemical reactions out there, and we need to be able to predict those products. So we might see a reaction where we have a more complicated reactant if this is a decomp, and we don't just get a B, we have to do something with this P as well, and it just puts a little bit of a wrinkle in how we predict those products. Luckily though, we still have some patterns for figuring out these reactions, and these are 3 hints that often happen. Notice how I say not always though, because we don't always see carbonate break down into carbon dioxide. We don't always see OH turn into H2O. We don't always see the ammonium ion turn into ammonia, but those are often what we do see. So these are helpful patterns to, in general, just be aware of and look out for. Now, the one thing to look out for, though, is that if you see CO3, I see students make the mistake of almost always putting CO2, but you have to keep CO3 unless if you are for sure in a special reaction pathway. So keep that in mind. Common mistake, students will break this down into CO2. That's not how it always works. So most of our special reactions for our class are the decomp and synthesis special reactions. We have a bunch of those to look at, so I have several slides on this. For decomp and synthesis on your brown sheet, we have these listed together because these are what we would call reversible reactions. So you can read right-hand side to left-hand side or left-hand side to right-hand side, depending on if you're talking about synthesis, 2 items turning into 1, or decomposition, 1 item turning into 2. So keep that in mind. We're using the generic term metal because that's anything left of our stair-step line, and then with a carbonate anion attached to it, turns into the same metal, so these have to be the same, and then oxide, and then carbon dioxide is the other product. So here we see magnesium and magnesium, the carbonate, carbon dioxide, there's that special reaction pathway, and then here's our oxide. This time we see sodium, notice it's sodium oxide, still checking our charges and crisscrossing like we learned how to do already, but we do see that CO2 product. Whoops. For the second reaction here, metal hydroxide, so like above, the metal has to stay the same on both sides of our arrow. We could take magnesium oxide with water and make magnesium hydroxide. We could make sodium oxide plus water and make sodium hydroxide. So this is, again, that special reaction pathway that we see. Getting into reactions 3 and 4, a metal chlorate, same thing as above, the metal needs to stay the same on both sides. If we take metal chlorate, that's going to break into a metal chloride. So notice that the O3 turns into O2 over here in this case. And we're still checking our charges on the metal chloride. Calcium chlorate turns into calcium chloride plus, and then oxygen fell onto the next line for me here. Number 4 is probably the most difficult because we have this ternary oxy acid, so we need to have a 3 or more atom acid. Oxy has to contain oxygen. It starts with hydrogen, there's our acid. Turns into a nonmetal oxide. So the nonmetal in this ternary oxy acid is carbon, and so we have a nonmetal oxide right here, carbon dioxide, that's our nonmetal oxide, and then water. The trick is, though, that we need to keep this guy, this carbon, with the same oxidation number. So when you break this down, you have to go back into the original compound and see what was my oxidation number on carbon. We learned how to do that with our oxidation number unit in our formulas and names for honors chem. For regular chem, I don't give you ones that change, so you don't have to worry about that. But you have to check your charge on carbon, and then when you make this product, you have to check your charge in crisscross, -2, and then with whatever charge this happens to be. And in this case, it's a +4. So we would have a 2 and a 4, and then we reduce that down. Over here, likewise, sulfur is in this case, it's a +6. So we have a 6 and a 2, which reduces down to a 1 and a 3. And that's why we have the SO3. Down here we have sulfur being a +4, so +4 minus 2, a 2 and a 4 reduces down to a 1 and a 2. So nonmetal oxide and water, if we start out with a ternary oxyacid, a little bit more work to do on these ones though. 5 and 6, we have ammonium hydroxide. So here again we see that special reaction pathway of OH turning into water, and then ammonium turning into ammonia. So here's our NH4 switching into our NH3, and here's our OH switching into our H2O. And again, if we took ammonia and water, we would also make ammonium hydroxide, because we can read this right-hand side to left-hand side as well. Also notice that this pathway is literally this example. This is the only way that number 5 works, whereas the previous ones, there was a variable depending on what nonmetal or what metal we were talking about for the previous 4 reactions. Let me go back. And then finally, ammonium carbonate turns into ammonia, carbon dioxide, and water. So here again, we see NH4 turning into NH3. We see CO3, the carbonate anion, turning into CO2. And then water gets peeled from here and here, and that's where we get the water from. And again, this is the one and only way that special reaction 6 goes. It's this example, and we could do it the opposite way as well. So then moving to the single replacement, we have 3 special single replacements. These ones aren't quite as special. They're more predictable in their pattern. Specifically, number 1 and 2 are a little bit more predictable. We have an active metal plus water, makes a metal hydroxide and hydrogen gas. And there's 2 examples of this: calcium, water, sodium, and water. But this has to be an active metal, which we're saying would be groups 1 and 2. We also have our gold sheet on the single replacement side. It needs to be a metal that's in the section that happens to be high enough up that it can react with water. So this one does not go left and right. It just goes from right-hand side to left-hand side. Or excuse me, left-hand side to right-hand side. I guess I'm too tired this morning. For these reactions, they're not reversible. Metal plus an acid. So here's my acid starting with H. Here's my metal element by itself. The magnesium switches with what it's similar to, which is the hydrogen, kicks out a hydrogen gas. So this is very predictable. When we say salt, that just means an ionic compound. And then our hydrogen gas, as you can see, don't forget that's a Hunkelbrief. Same set of rules, check your charges, crisscross, and all that. See the same thing right here. Zinc switches with the hydrogen. Hydrogen's right there. We get zinc sulfate plus 2 minus 2. That's a good formula. Finally, this is the more difficult of the single replacement specials. You have a metal hydroxide, so calcium hydroxide with your carbon dioxide, and there that is. Carbon dioxide, because that's that special reaction pathway where it's also similar to CO3, and CO3 is an anion, CO2 switches with the anion. So these kind of behave similarly, and we make a carbonate right here, and this turns into a water, and there's our carbonate and there's our water. So that's what happens there. The lone particle switches with a similar particle. Still follows that same pattern. It's just that the particle is no longer an element, it's a whole substance, and it behaves like an anion when it's reacting. So that was the decomp synthesis and single replacement. And then the last group are the double replacements. We have an acid-base neutralization, and this one's not overly complicated because we're still switching our cations. So calcium and hydrogen in this case are the cations. Here's my acid, here's my base, acid base. We know it's an acid because it starts with H. This one we haven't talked about as much. For this definition, OH is our base group. So hydrogen and calcium switch spots. If calcium is sitting in front of sulfate, that's this compound, and then if H is sitting in front of OH, that's HOH, which we can change and rewrite as H2O, water. Still need to check your charges on your ionic, but water, of course, is just always going to be H2O, and then balance and crisscross and all that stuff. The little bit more complicated double replacements is this idea that if we happen to form one of these 3 products, we are automatically going to break that product down. So our 3 products that we form are ternary oxyacid, ammonium hydroxide, and then ammonium carbonate. And that should be a 3 right there, not a 2. That's a typo on my part. And the thing with these are decomp/synthesis numbers 4, 5, and 6. So we've actually seen these reactions if we make a ternary oxyacid, we make it into a nonmetal oxide and water. That's right here. If we make a ammonium hydroxide, we make a ammonia and water. And then if we make an ammonium carbonate, we break that down into its three parts, which are ammonia, carbon dioxide, and water right here. So those break down into those pieces if we make them. So the key here is you need to say I have a double replacement. I need to check if one of my products happens to be one of these three. So overall, when you're working on these, once you identify that it's not just a straight up typical follow the pattern reaction, and I have those questions that can get you there, you need to identify what is my metal, if it's a synthesis or decomp, assuming that it's not a 4, 5, or 6 where it's a ternary oxyacid breaking down or ammonium hydroxide or the ammonium carbonate. You need to find your metal and then find the pathway on your brown sheet. If it's a a single replacement reaction, you need to figure out which one it is. The first two are much easier to figure out. The last one, you see that carbon dioxide, you're going to know that it's going to be that third special reaction. And then for the double replacements, specifically, if it's not the acid-base neutralization, you're looking for, do I have a ternary oxyacid? Am I making ammonium hydroxide? Am I making ammonium carbonate? You just need to kind of memorize these three as products to look out for and be aware that you need to just look. That's the key here. So after this discussion, I hope that you learned that there are special reactions and they do follow some patterns that almost always work, but not always, not 100%. And we have a resource that helps us figure out what those products might be. You still follow the same predicting product steps like checking your charges, crisscrossing, looking for Hunkelbriefs, and balancing chemical equations. But when we make those simple products, we have some patterns that we need to follow that are predictable patterns once you can identify which pattern you're using. So I hope that helps, and good luck on working on these.